Okay, so today we shall read. mm, Today is lecture. Today is lecture 4. Today we shall read cross correlation. Cross correlation plus we shall read strict sense stationarity plus we shall read wide sense stationarity. All those things. Okay. So now let's see. So first we'll see our. So in the last class we have seen that we characterize a okay. So last class we characterize a single random process, how we can characterize it, and now in this class we will see that how we can characterize a a two random process, multi-random process. We will take two, not more than that. So we can characterize the two random processes. So let's say, so earlier what we have seen, now we have, earlier we have seen we have a random process, a random process, a random process xt, and we have another random process, another random process yt. Now, how we can characterize both? So we need to know the PDF of all possible combination of samples from xt and yt. So to characterize xt and yt jointly, to characterize xt and yt jointly, we need the PDF of all possible combination of samples from xt and yt. So we need PDF of all possible combination of samples from xt and yt. So what does it mean? So it means that we need to characterize the joint distribution of samples from xt and sample from yt. Okay, so for example, so if we have sample xt, say we have sample xt, we took sample xt from xt at the time t1, t2, t3, like tk, and we take the sample population yt at the time say t1 dash, t2 dash, okay, tl dash. Okay, so and then we need to know the joint PDF. Let's say the joint PDF of x and y. So the joint PDF of xt and yt, we can define xt and yt at those times can be written as, so f of first this one xt1, xt2, okay, xtk, and then y t1, sorry, yt1, yt2, t1 dash, yt2 dash, y tl dash, and x1, x2, xk, comma y1, y2, YL. So if we know this joint PDF of X of time T1, T2, T3 dot Tk and Y of time T1 dash T2 dash dot TL dash, this joint PDF, if we know, we can say that we have characterized the two random processes together. Okay, but it is still again very difficult to do that what we have discussed earlier. So what we can characterize it, we can characterize in terms of the cross correlation and cross covariance. So what will be the cross correlation? So now the cross term is coming. Why cross? The cross means we are taking X and Y both. We are taking X and Y both. That is why we are taking it a cross. So what will be cross correlation? Cross correlation. So cross correlation will be R X Y, X Y both will come, and at the two time step Ty, Ti, comma Tj, what it will be, how we can define it? We can define it as the E of X Ti and Y Tj. Okay, earlier we have seen the auto, that means in the same process. Now we are seeing the cross, that means the between the two process and two different times instant. We can define the cross covariance as Cxy Ti, comma Tj will be equals to E of X Ti minus mu X Ti to Y Tj minus mu Y Tj, this one, and this can again be proved as it will be Rxy Ti, comma Tj minus mu X Ti into mu Y Tj, right? So if what is the physical significance of cross covariance? If Cxy equals to 0 or Cxy at two time Ti, comma Tj equals to 0 for all Ti, comma Tj, we say that the process Xt and Yt are uncorrelated. Okay, the process Xt and Yt are uncorrelated. You see that it will be 0, then Rxy will be mu x into mu y. So this will be uncorrelated. So the uncorrelated does not mean the process have, it means the process has zero covariance, but it does not mean that it has a zero correlation. So the uncorrelated means, so is uncorrelated. So uncorrelated means the process has zero covariance. It means, so uncorrelated means the process has zero covariance. So the same thing we can write in the discrete time case. So only the t will be substituted by the n. So how we can write in discrete time case? In discrete time process, where the time is in a discrete process, we can write as a discrete time process, we can write Rxy Ni, comma Nj will be equals to E of Xni to Xnj. Okay. Similarly, we can write Cxy Ni, comma Nj Nij means like this, n1, n2, n3. We don't have all the time because it's the discrete time, so we have n1 time, n2 time, n3 time, like this. So n1 comma nj, it will be equals to e of x t ni minus mu x ni into y of nj minus mu y nj. That's it. So this we can write, or similarly equals to x my ni comma nj minus mu x ni to mu y nj. Okay, this is the whole point. Now the next we shall move the next topic. What do you mean by strict sense stationarity? We shall go, what is the meaning of strict sense? When a random process becomes strict sense stationarity, or random process is stationary in strict sense. Stationary. So that means a random process will be stationary in strict sense. Okay, when it will be, let's say we have a random process, we have a realization, we have the ensemble, and we take the samples at over the ensemble. At the time we take the samples, over the ensemble at time t1, t2 tk. Okay, and we calculate the joint distribution, and the joint distribution of them, joint PDF of them will be f of x t1 x t2 x tk x1 comma x2 xk. This is the joint distribution of, we take the sample over t1, we take the sample of ensemble over t2, we take the sample over the ensemble at t3, like that we take, and we calculate the joint distribution. So this joint distribution can be written as with this expression f of this. And then what we do, we calculate, we take the same distribution, joint distribution, calculate the joint distribution after the time shift of tau. So what is the meaning? Meaning is, suppose we have a like ensemble of this, so we have t versus x1, we have t versus x2, like this we have t versus xn. Okay, so it is like this. Okay, and we calculate, we take at t1, we take t2, like this we take tk, and then we shift the time tau. That means we take at some point, say t1 plus tau, then t2 plus tau, then tk plus tau. Similarly we take all those, t1 plus tau, we take t1 plus tau, we take t2 plus tau, we take tk plus tau, right? And then we calculate again the joint distribution. So then we shift whole time by tau, and express the PDF at the shifted time. So what will be the PDF? So the PDF will be f of xt1 xt2 dot 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 sorry f of the PDF will be f of xt1 plus tau okay comma xt2 plus tau comma dot 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 xt k plus tau of x1 t1 plus tau x1 x2 x3 dot 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 xk, and if both the PDF are same, what does it mean? That means before time shift, or if the PDF are same, or if the PDF remain same, or if the joint PDF remains same after the time shift tau, means that f of x t1 x t2 dot 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 x tk of x1 comma x2 dot dot xk will be equals to f of x t1 plus tau comma dot 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 x tk plus tau in bracket x1 x2 dot 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 xk. If both are same, the random process is called strict sense stationary process. Okay, so do you understand what is the strict sense stationary? Strict sense stationary is we have taken that up to t1 t2 like this tk, and then ensemble population over the ensemble, and we calculate the joint PDF, right? And then we shift the whole things over the tau, and then again we calculate the joint PDF after the shifting. If both are same, then the process is strict sense stationary. Now in many places you will see in many books, so they are characterizing it like the first order stationary process, or first order strict sense stationary process, second order strict sense stationary process, like that. So we can also tell that based on the k, if we take only one time sample, one time instant t1, that is first order stationary process. If we take the two time samples t1 and t2, it becomes a second order stationary process, so and so on. So it's very simple, but still we will mention. So first order stationary, first order strict sense stationary process. So what does it mean? It's very simple. If we take the ensemble at any time t1, and we take the ensemble after shifting it tau, so x of t1 plus tau x1, if both are same, we call it is a first order stationary process. Now what is the second order SSS process? Second order SSS process, very simple. We will take the two time step, two time instant, so ensemble over the two time instant. So f of x, okay, t1 comma x t2 and x1 comma x2 will be equals to f of x t1 plus tau x t2 plus tau x1 comma x2. Then this is called the second order stationary process. SSS process, and kth order SSS process is the same what we wrote earlier. Again we'll write, so fx t1 comma xt2 comma xtk of x1 x2 xk will be equals to f of x t1 plus tau x t2 plus tau x tk plus tau x1 x2 xk. Then this is called the kth order SSS process, right? Now what would be the example of SSS process? Okay, so it's a very restricted process, and what would be the example? So example, a IID process is a SSS process. What is IID? IID, the IID sample. So first let us tell me IID means identical and independent and identical distribution. Independent and identical distribution. Independent and identical distribution. What is that? Suppose we have a sensor. Okay, so sensor generally measures the noise, measures the physical parameter. Suppose we have a sensor, it's measuring some physical parameter, and no sensor is perfect. So, and the sensor measurement is corrupted with the noise. And let's say the noise is a IID process following a distribution. So sensor measurement, so what we will get? So output will be or sensor output will be the exact value of the physical parameters, say temperature, pressure, all those things, humidity, okay, angle, then range, okay, distance, plus noise. Okay, so let us assume that the noise is following. So let us assume that the noise is following a PDF, say Gaussian. PDF. Noise is following a PDF, say Gaussian PDF. And also we assume that the process is RP is discrete time. That means the time is discretized. Is discrete time process. That means the time is discretized. We don't have all the value of the time. We have the values where we sample it. So such a process is widely used in modeling. So such a process is widely used in modeling and in engineering. So what will be, let's say we take the N1, N2 like that in L. So we take it that fx of N1, okay, x of N2 x in k, okay, of x1 x2 xk, and then after the time shift we take it again, and all will be the same because it is IID process, it's independent and identical distribution. So it will be f of x n1 plus tau x n2 plus tau dot x in k plus tau x1 x2 xk, and this will be same. So if we take at n1 instant, okay, and then again we take the n1 plus tau instant, and we take the PDF of it, and we take the PDF of it, and both will be the same distribution because it is independent of in one cluster and identical distribution. It's following IID sample. So this is an example of example of strict sense stationary process. Okay. Now let's discuss about what do you mean the wide sense stationary process. So what is the wide sense stationary process? Wide sense stationary process. So this is a less restricted type of stationarity. This is the SSS is the more restricted type of stationarity, and this is WSS, we call it WSS. So WSS is a less restricted type of stationarity, less restricted type of stationarity. And what is that? So suppose if the mean value is independent of time and autocorrelation is only the depends on the time difference, then the process is called the wide sense stationary process. We have to draw a figure, otherwise we cannot explain it. Let's say we draw a few single realizations. Say this is t versus x1. Now let's see, this is t versus x2. Similar it will go on. Let's say we have t versus xn or something. Like this. So let's say we at any point of time ti, let's say we take any point of time ti, t1 or something, we can say ti, right? What we have x1 of ti, we have x2 of ti, we have xn of ti, right? And then we take all the values of over the ensemble and we do the mean of it. So mean of it. What does it mean? Mean of it and mean of this. And let's say we got a mean mu x which is independent of time. Okay, that means whatever time t1 or t2, so you take the mean mu x which is independent of time. That means if you take another interval tj, another point tj, and you take the mean of it, again the mean will be mu x. Okay, so that means mean is independent of time. Whatever time stamp you take, okay, whatever time point you take and calculate the mean over the ensemble, it remains fixed. This is the first point, it remains fixed. You take the mean of over the ensemble at any time, and then that mean will be same and fixed. Will be same. That means it will be fixed, will not change over time. This is the mean property. Next is, let's say we have similar type of process. So we have t versus x1, t versus x2, we have t versus xn. Okay, and then we take one time t1, we take time say ti, and we know what will be x1 ti, x2 ti, xn ti, and then you take another time tj, we know what will be x1 tj, we know what will be x2 tj, we know what will be xn tj. Okay, then you shift it both the cases with tau. That means you take a shift of this over tau. That means this point you take ti plus tau. Okay, this point you take ti plus tau, this point you take ti plus tau. Again you shift tj, you take tj plus tau, you take tj plus tau, you take tj plus tau. Okay, now so you have four set of samples population, now you calculate autocorrelation, you calculate the autocorrelation among these two sets. So you calculate autocorrelation, then what you will get, x or xx ti comma tj, right? And then here also you calculate the autocorrelation, both the cases after shifting autocorrelation. You calculate the autocorrelation rxx ti plus tau comma tj plus tau, right? After shifting you take the autocorrelation. Now if the autocorrelation is only depends on the difference of shifting, that means the tau, if the autocorrelation only depends on tau. Okay, that means if the autocorrelation only depends on tau, that means the shift of both the time, okay, only depends on tau, not whatever the time we are considering. Okay, so we call the process as WSS. Okay, so mathematically how we can write? Let's write the mathematically. So a process is said to be WSS if a process is said to be WSS if E of xt at any point of time, you take E of xt, maybe t1, maybe t2, whatever, xt will be equals to mu x. You note it, there is no argument of t, that means constant. Okay, there is no argument of t. This is the first criteria. Next is if rxx ti comma tj will be equals to, so yes, so both are same if both are equal. So rxx ti comma tj will be equals to rxx ti plus tau comma tj plus tau for all tau will be equals to rxx ti minus tj. Okay, so let's do one thing. Don't tell it tau, because tau generally we take. This is not, don't tell it tau. You write say alpha, you write say alpha. Okay, you write say alpha 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 alpha. Okay, t1 plus alpha tj plus alpha. Okay, if the autocorrelation function depends on tau equals to ti minus tj, we call it the WSS. Okay, so it is said to be the EXX of this, and this will be equals to RXX of tau. This is called alpha. This is equal alpha for all alpha. So equals to Rxx ti minus tj will equals to Rxx tau. That means the autocorrelation function between the two times only depends on the difference between the time, not exactly the time. Okay, exactly the two times. So if these two conditions holds, then the process is called a WSS process. So again, let me tell what are the two conditions. So first condition is you take any time and then you take the ensemble and do the ensemble average. You will get a fixed number, not the function of time. Okay, whatever time you take, you get a fixed number, same number every time you get. This is the first thing. Next thing is you take the two times time and ensemble. You calculate the autocorrelation. And if this autocorrelation, and then you take another two times time, you calculate the autocorrelation. If the autocorrelation depends only the difference of the two time, okay, difference between the two times, not the different two times, only the difference in time. If these two things holds, then the process is called the WSS. Okay, then the process is called the WSS process. So let's give one example, then it will be clear more. So example, let's say a process is xt will be equals to a sine or cos, let's say a cos omega t minus theta, where theta is from uniform distribution of 0 to 2 pi. Okay, now tell me if this process is white WSS or not. Okay, solution. So what will be the ensemble average? So expectation of xt over the ensemble will be equals to the a cos omega t minus theta over any time t, and we have the distribution of theta, which is say f theta, then we have d theta, and then we have to integrate in between 0 to 2 pi, because the distribution limit is 0 to 2 pi. What is the distribution? Distribution is a uniform distribution. So, and you have a uniform distribution of 0 to 2 pi. So we can write it that a, so a by 2 pi 0 to 2 pi cos, because f theta is a by 2 pi, it's a constant, cos omega t minus theta d theta will be equals to 0. So you see the expectation, one condition is getting satisfied, that expectation of t is independent of time and it's a constant, so we are getting it. Then let's see another condition, whether it is satisfied or not. We need to calculate e of xt and xt plus tau. At one time t we are calculating, then again shifting t plus tau, okay, and then we are trying to calculate the both tau. So this will be equals to a cos omega t minus theta cos omega t plus tau minus theta f theta d theta 0 to 2 pi. So what we are getting? We are getting a again a square. So 1 by 2 pi a square 0 to 2 pi cos omega t minus theta to cos omega t plus omega tau minus theta d theta will be equals to 1 by 2 pi a square into 1 by 2 0 to 2 pi cos a cos b, cos of 2 omega t plus omega tau minus 2 theta plus cos of omega tau into d theta. Now you see will be equals to 0 to 2 pi 0, so this will be 1 by 2 pi a square 1 by 2 into pi by 2 a square is written cos, this cos omega t will go out, omega tau, okay, and then this one will be 0, so cos omega tau into 2 pi cos omega tau into 0 to 2 pi 2 pi. So 2 will cancel out, it will be half, pi will cancel out, half a square cos omega tau. So you see that e is, so this is a function of tau. So the process is WSS, wide sense stationary process. So the process is WSS. Now if we take another example 2, we have taken that a xt will be equals to a sine omega t, where a is in between 0 to 1, uniform distribution. So clearly if you see that e of xt is not constant, right? So it is not WSS process. If you take another example, let xt will be equals to at plus b, where a and b are independent random variables, both So a uniform distribution follows the uniform distribution of -1 +1. So whether this is a WSS or not, wide scene stationary or not. Solution. Let's calculate E of xt will be equals to E of AT plus B will be equals to E of A T plus E of B will be equals to 0 plus 0 equals to 0. This is a constant, so one condition is satisfied. Now let's see what will be Rxx of t comma t plus tau. So this will be E of AT plus B into AT plus A tau plus B will be equals to E of A square into t square and E of AT, that means t into A square t plus tau plus ABT twice ABT plus B square. This will be equals to E of A square into t plus tau plus E of 2AB into t plus E of B square will be equals to E of A square means it is both a square, it's not 0. Okay, so it will be 1/3 t into t plus tau plus E of B square will be equals to 1/3 E of 2AB. This will be 0, so this will be equals to 1/3 t square plus t tau plus 1. So clearly it is not a function of tau, so it is not depends only tau, rather it depends on t also. So the random process is not WSS. Okay, so we learn it. Next class we'll do the ergodic process. Okay, so today we stop here. Thank you all of you. Okay, bye.